3 is here, 3 times 2, right? And then 3 is here, but twice, 3 times 3. And then 3 is here, and so on, right? So we can count the number of 3 appearing in the factorization of n factorial, right? When you factorize n factorial, 3 appears here, and then 3 appears here with 2 times 3, and then 3 appears here twice, 3 times 3, and then 3 appears here 1 time. And we have these things, and then we can count the number of boxes, and then somewhere 3 to the power of 3 may appear, right? 3 to the power of 2 appears in this. So in this row, 3 to the power of 1 appears here. 3 to the power of 2 term appears, and then 3 to the power of 3 appears in this order. Then we want to count the number of boxes. Then from this point to this point, we have n over 3 floor function of n over 3 boxes. Do you get it? We have floor function of n over 3. Why? Because we divide the length n by 3, then we will get 3, 3, 3, and this one. And then for these boxes, we have n over 9, or 3 squared. And for these boxes, we need n over 3 cubed, and so on. So eventually, to get the factor 3, we need to add all these numbers, because 3 happens twice, 3 happens 3 times, 4 times, and so on. So for each 3, when you want to calculate the exponent, this exponent equals n over 3 squared, n over 3 cubed, all the way. And it cannot go forever, because somewhere after these things, this denominator will exceed, right? Exceed n. N is a fixed integer, so the denominator will exceed. Then the numerator over denominator will be smaller than 1. Then the floor function of some number smaller than 1, between 0 and 1 I mean, should become 0. So 0 is added. So even if we use the infinite expression, this is a finite sum. It converges. So we can always find this number. And this one is necessary in the following proofs. But for instance, if you are asked to find number of 2's, then you need to do something like these, right? You need to do something like these, right? When you need to find number of 5's, then you need to do these things. But obvious observation, as you can see, what prime has more appearance, 2 or 5? Smaller prime or bigger prime? Smaller prime appears often, right? So for instance, if you are asked to find the number of 10's, 10 is not prime. 10 is a composite number. Then we should decompose these things into primes. 2 times 5, then 2, and then 5. So to count this 10, power of 10, we need to consider power of 2's and power of 5's. But as you can see, 5 is far less than, the exponent of 5 is far less than the exponent of 2. So what dominates this, what determines this power? What determines this power? Exponent of 5 or exponent of 2? Exponent of 5 will determine the exponent of 10, because assume that you have, for instance, 100 2's, but only like 25, or maybe 25's, right? Then we can only combine at best 20 times, right? We can combine 2 and 5 at most 20 times. Do you get it? That means to determine the power of 10, we should check the power of 5 because it has 2 has more exponent that we can always use. But 5 is limited, right? The resource of 5 is limited. So for instance, I will give you a problem. For instance, you may pick any big number. 51 factorial. Then 51 factorial will be something, and then after these things, zeros will follow. Then how many zeros will follow? So this is the question. Then to count the number of zeros, we should count the power to the base 10. That means we should count the power to the base 5. Do you get it? So we should count the exponent to the 5, to the base 5, right? So let's do it. 51 over 5, 51 over 5 squared, 51 over 5 cubed, and so on. And then as you can see, if you divide 50 by 5, then 10. 10.2, floor function of 10.2 is 10. And then 51 divided by 25 is 2 point something, so it is 2. And then 0, and then 0, and then 0. So because of this region, there should be 12 zeros. If you consider 51 factorial, there will be 12 zeros. Do you get it? Because to make 10, we need enough 5s. If you don't have enough 5s, even if you have very many 2s, it doesn't count, right? The 2s do not count. Only the exponent to the 5 determines the exponent to the 10. Do you see the reasoning? Or do you understand the reasoning? Or not? So how many zeros can you count in 51 factorial? Then the answer is 12 zeros. If you don't have any question, then I will cover some theoretical things instead of calculational things. No problem. You may pick any number. 31 factorial, then 31, and so on. And then as you can see, 31 divided by 6, and then this divided by 25 is 1, and then 0. So it means total 7 zeros. 7 zeros will follow. So the number of zeros, meaning 10 to the power of something. The exponent to the base 10 is determined by the exponent to the base 5. And then if we count the exponent to the base 5, then it's enough. What about base to the 2? There are enough 2's that we can use to make 10s. For instance, 31 over 2, 31 over 2 squared, 31 over 2 cubed, and then 31 over 16, and then 31 over 32 is 0, right? So if you count these things, 15, and then 7, and then about 3, and then about 1. So there are total 26 2's. So we can combine 26 2's and then 7 5's. So there is excess 2's that we cannot use to compose 10, right? To compose 10, we have enough 2's like 26 2's and then 7 5's. Then this excess 2's cannot make 10 because only 7 will work. Then we can, as you can see, 10 to the power of 7, right? So it's not equal, but it indicates, right? Then there are 7 zeros. So when you have 31 factorial, then we will have 7 zeros. Unless you have a question, I will cover theoretical things. Floor function satisfy this thing. A plus B floor function is greater than or equal to A floor function plus B floor function. And for instance, consider you may pick any number. 5.6, B is 4.5. Assume that we have these two numbers. Then A plus B is what? 10 plus 1, right? 10 plus 1 is what? 10. What about floor function of A? Floor function of A is 5. What about floor function of B? 4. So floor function of A plus floor function of B is 9. So as you can see, 10 is greater than 9. So when you have addition and then floor function, then that is bigger than separate floor function and addition later. Using this, we can prove the following fact and assume that I questioned this on the exam, then you would need to use the above fact. Prove that this is an integer. So for any n, for any integers satisfying these things, prove that this is an integer. Then someone may say, oh, because of binomial theorem, this is an integer or something. But what I want is a proof, not the statement. So proof. N choose R, by definition, is n factorial, and then R factorial, and then n minus R factorial. Then, as you can see, we can write these things using P1 to the power of something, P2 to the power of something, P3 to the power of something, and so on, right? And then we can write down the denominator by P1 to the power of something, P2 to the power of something, P3 to the power of something. Do you get it? So we can factorize the numerator and factorize the denominator by using P1 through P something. We don't need infinitely many primes, just finite number of primes will cover n factorial or the denominator. Any questions about this? Then let's pick generic P here. So pick some generic P. So P to the power of something in the numerator, and then P to the power of something in the denominator will be calculated. So if we focus on generic P to the power of something in the numerator is n over P floor function, right? And then n over P squared, and so on. So this is the floor function, right? This is the power of P in the numerator. The same thing can be calculated in the denominator. In the denominator, R over P for the first part, and then I will use two rows, n minus R over P. And then the next number is R over P squared, R over P cubed, and so on. And then here, n minus R over P squared, n minus R over P cubed, and so on. Any questions about this direction? So we have numerator over denominator, and then we want to find the power of p for the numerator and the power of p for the denominator. Now let's compare. If you add r plus m minus r, it is what? Obvious calculation. Do you see it? N, right? So take a look. If you compare column by column, if you compare these three things, then these two addition, and then the addition of this numerator is here. Do you see it? Because of the fact that I mentioned, n over p to the power of anything is greater than or equal to r over p to the power of anything, and then m minus r over p to the power of anything. So, as you can see, if you write the numerator using prime powers and the denominator using prime powers, then n factorial, r factorial, m minus r factorial will have somewhere p to the power of something here, and then somewhere p to the power of something here, and then this power exceeds the power in the denominator for generic p. No matter what p you pick, this means we can cancel out these things, and it may still have some power. So after canceling out, we will have these things, not just for this p is generic for any p. In other words, after doing this division, the denominator will be canceled out, completely canceled out because of this fact. Because power, so let's give name. Let's give a name to this sum. So the power for the numerator is called Pn. Power for the denominator is called Pd. So as you can see, Pn power, right? Pd power. Pn is greater than Pd, greater than or equal to Pd. So eventually what we will get is Pn minus Pd, and which is positive or non-negative, right? Which is non-negative for generic P. So because of this reason, prime is an integer to the positive or non-negative power all the way through on the right side, and then this proves that binomial coefficient is an integer. So I completely proved it, and if you have a question, ask. The next thing is this. Prove that r factorial divides product of any r consecutive positive integers. So pick any r consecutive positive integers. For instance, three consecutive integers, n, n plus 1, n plus 2. Then, because of this fact, it is divided by what? 3 factorial, or 6, right? If you pick 4 numbers, n, n plus 1, n plus 2, n plus 3, then because of this fact, it is divided by what? 24. If you pick 5 consecutive numbers, then it is divided by what? 120. And all these can be proved by the same fact. So let's test it. Let's test the case using computer software. So we may pick for instance, any number. You should start off with any number. What number do you want? Product equals, you may pick any consecutive number, product of what numbers? Like 8 through 12. Do you see? So product of 8 through 12 is called PRD. So I will do it. And this number. Then 8 through 12, how many consecutive numbers can you count? 8, 10, 11, 12. 5 consecutive numbers. Then it is divisible. It is divided by 5 factorial. 5 factorial is what? Thank you. It is 120. So let's divide PRD divided by 120 integer. So let's do it one more time. Instead of 8 through 12, let's do 4 through 12. 4 through 12 is this number. How many integers can you count? 4, 5, 6, 7, 8, 9, 10, 11, 12. Total 9 integers, right? So I will divide this product by 9 factorial integer. Of course, it can be divided by 10. It can be divided by 10 factorial of 11. 11 factorial is possible, right? But at least 9 factorial divide. But as you can see, 10 will divide it, 11 will divide it. So it is divided by 11 factorial, but the theorem guarantees 9 consecutive number means 9 factorial, no matter what number you pick. What consecutive numbers you pick, we can do. So we saw some strange fact, and as I mentioned before, we cannot publish a paper by doing just this kind of research from, for instance, 1 through 1 million. And then I write a paper and send it, then it will be rejected. Because that huge, like bigger than phone book paper doesn't count in mathematics, because you should prove for the whole set of numbers, not for 1 through 1 million. So I found some fact for 1 through 1 million. No, we should prove to all cases, not just 1 through 1 million. So let's do it. Product of any consecutive integer. So let's start with, for instance, k, right? K is the starting number. And then k plus 1 up to k plus r minus 1, right? So total r numbers, right? K 0, right? 0, 1, 2, 3, and then r minus total r numbers. Then we can create this kind of fraction. Then the statement is, the claim is, this is an integer. This is an integer. So, as you can see, we can write this kind of statement. K, I don't have enough space, so I will write it upstairs instead of downstairs. We can regard this as k plus r minus 1 factorial, k plus r minus 1 factorial. Then because we assume that there is more factors here, we should cancel out those factors up to what factorial? K minus 1 factorial. Right? This portion represents the numerator, and then now the denominator is attached. So I rewrote I rewrote this statement using factorial notation. Do you see? So this left side portion is cancelled out by this one, right? And then we can write it. Then now, after this, we can write this thing using binomial representation. And I proved that this is an integer. So this is an integer. Done. And all these proofs come from very simple counting. So as I mentioned before, in number theory, we cover very, very easy and straightforward fact. And then we prove each small fact. And then using small things, we claim big things. And as you can see, all started with simple counting of factors such as 3, right? 3 happens here, 3 happens here, 3 happens twice here, and then 27, 3 happens 3 times here, right? 27, 3 happens 3 times, and so on. So we count these things by accumulating these possible numbers, and then we calculate the exponent. Very simple idea. And using this simple idea, we can count the number of zeros, and we can prove that, we could prove that this binomial coefficient is an integer, and then we also prove that any r consecutive positive integers are divided by r factorial. So this is the summary, and if you have a question, ask. Then let's go to the next example or theorem. Excuse me. The next example is very straightforward fact. Assume that we call the sum capital F. So we call the sum of lowercase f by capital F, then what if we sum these f? So what will happen? Or instead of infinity, I will limit this thing to a specific number such as capital N. So what if we add the left side from 1 through n? Very, very similar idea to the previous one in the proof. So this means summing these things. But if you are not familiar with this expression, then it will be very tough to understand. So instead of using this summing expression, I will use straightforward expression. F1 equals lowercase f1, because 1 is the only divisor of 1. Do you see it? If you don't, ask me. What is f2? F2 is, the divisor of 2 is 1 and 2. By definition here I wrote it. If you don't understand, ask me. If you have f of 2, then it means f of 1 and 2. Do you see? F of 3, then f of 1, then f of 3, and as you can see, 2 is missing. So we have a definition, capital F, and then we are writing these things because we will sum the left column from 1 through capital N. And f of 4, then it is f of 1, f of 2, and then f of 4. So we can continue writing these things. And then once we go all the way down, then f of capital N equals f of 1 and something in between, and then f of n. Now we are summing these things. And in the previous example, how did we add the exponent? We add it by rows, right? By rows. And in this case, we are adding by columns. We are adding by columns. Then as you can see, we add these columns. Then this sum becomes the left side. Do you see it? The left side. And then we are adding these things, then how many f1s appear? Total n, right? So f1 appears total n times, or n can be written n over 1, right? N over 1. Do you see it? N appears n over 1. I am summing column by column. And then I want to add the second column. Then the second column appears every other time, right? Because when we have odd n, we cannot have that 2. But when you have even n, we always have 2. So every other time. So how can you count it? So f of 2 appears total how many times? N over 2 times. Do you see it? What about 3? It should appear every 3 times, right? So f of 3 appears every 3 times, and 4 appears every 4 times. It's obvious, right? It's very obvious. So for generic k, f of k appears every how many times? K times. And so, right? All the way up to f of n, right? F of n, and then n divided by n. 1 time, right? The final time. Only final time. So, as you can see, if we write the sum in the given order, we don't see any special thing. But if we change the order of the sum, instead of row by row, we did it column by column, then we get a strange result. And then we can claim the result. So I can write the result. In fact, this itself is a result, but I can use sigma expression to write down this. Write down this result. Instead of saying dots or these things, I will use just sigma expression. And the left-hand side sigma expression is f of k running from 1 through n, or n running from 1 through n, equals sum of f of k n over k. As you can see, running variable can be anything that do not appear in other portion. For instance, you can use capital Y, X, or T, anything, right? So I rewrote this statement after constructing the proof, and I rewrote the statement. So in number theory, when you are asked to prove something, sometimes you have 2 sums, 2 sigma expression. Then the great technique is changing the order of the sum. Changing. I already did it before to prove the Mobius inversion formula. And in other cases, you can use the same idea. So I will use this fact to prove a few other things. I am adding these things from 1 through n. But no, you should know the fact. Tau n, or generally sigma 0 n, is nothing but the sum of ones for divisors, right? Do you see? So the number of divisors is defined by the sum of ones. Each time it divides, it adds 1. So this is the fact. Then with this thing, how can you write it? Then it is this. K running from 1 through n. And then this function is called lowercase f, right? This function is called lowercase f, f of d, right? This is f of d, but it is constant function, so d doesn't count, just 1. So 1, and then multiply by n over k. So this is the fact. Straightforward application. In other words, I, in fact, proved this thing, right? Tau n is this. Assume that we change this to sigma n. As usual, sigma n is sigma 1n, right? Sigma n is sigma 1n, and it is d to the power of 1. And in fact, we can regard this as d to the power of 0. D to the power of 0 is 1 all the time, right? So d to the power of 0, d to the power of 1, d to the power of 2, and so on. Then, because of this, it is k n over k. And as I mentioned before, k is a running variable, and that's this k can be replaced by any letter. For instance, lowercase n, y, x, anything, right? Then my next question is this. What is, instead of zeros or first power, s power, power of s. In other words, instead of this, assume that we replace this by s. Assume that what will be the result of this thing? Then it is equal to, because I don't want to break the pi with this k, I will replace this k with the letter that you pick now. You may pick any letter. What letter do you want to use instead of k? T. So t running from 1 through n, t to the power of s, n over t. T can be replaced by any letter not used in the formula, right? Any letter not used in formula. So we can do these kind of things. So this is the end of the chapter 6. And unless you have a question, we will cover the next chapter, which is very, very important in theory. Yes?
When are you going to start putting some sample examples?
I am making these things in this week. So once everything is made, I will post the things. So the next chapter is Euler's generalization, and the function that we will consider is Euler phi function. Sometimes this is called quotient function. Euler phi function is defined by very simple counting. Euler-Free function is the number of numbers, the number of integers, right? The number of numbers which satisfy number of integers really satisfy this condition, and so the number of numbers satisfying this condition, it should not exceed number of, we should be precise, positive integers, right? Number of positive integers satisfying these conditions, it should not exceed n. For instance, what is phi of 10? Then the possible candidates are number 1 through 10. It cannot exceed 10. Do you see? And then second thing is satisfying this condition, or in description we call the number relatively prime. The number should be relatively prime to the given number n, right? So relatively prime to n. So these two conditions should be satisfied. So for instance, 1. Phi of 1. What is it? 1 doesn't exceed 1, right? And then 1, and then 1, GCD is 1. What is phi of 2? Positive integer satisfying both conditions 1. Because if you use 2 here, then 2 GCD 2 is what? 2, so it cannot be. Phi of 3. One and 2 satisfy the condition, right? Phi of 4. 2, right? 1 and 3 satisfied it. If you don't follow me, stop me. Phi of 5. Total 4 numbers, right? 1 satisfies. 2, GCD is 1, right? 3, GCD is 1. 4, GCD is 1. 5, no. So total 4 numbers. Phi of 6. 1 satisfies, 2 cannot, 3 cannot, 4 cannot, 5 satisfies. So total 2 numbers. 6 cannot, so 2. So as you can see, is phi an increasing function or not? Is phi an increasing function or not? It's not an increasing function. Bigger number doesn't guarantee the bigger output, right? Bigger input doesn't guarantee the bigger output. So I want you to practice and then write down these things. And if you can write down these things without any mistake, it will be great. So please practice things up to 13. Of course, I will write down the correct result, or I will run the computer program to show you the result. I said 13, but I will give one bonus. So please calculate accurately. So do you get this result or not? If you didn't, please let me know. In my life, I've never counted above 10. If anything above 10 is required, I either use software or make one. In MATLAB, there is no phi function. I even searched the internet. Nobody created one, so I created one. So this is a question that is interesting. What year is it now? What year? Year 2001? So can you guess the result? No, you cannot. So phi of 2008. So phi of 2008 is, so it's millennium, right? This year is Euler millennium. So this phi function is studied. But if you have found some fact like or theorem like phenomenon, please let me know. Anything is okay. For instance, it is not increasing as I mentioned before. Do you see other things? Prime, right? Prime. Great. So prime number is like 7, 11, 13, or even 2, 3, right? Prime minus 1. Great. What else can you find? Even and odd thing. So strip up top two numbers and then check it. All even, right? Except top two numbers, right? So phi is even except top two numbers. In other words, if n is greater than or greater than 2, then phi of n is always even. So these kind of facts. So we will study these things. But in any case, this is very, very important in modern encryption. This algorithm is embedded in your web browser. And if you are interested in the coding of this, then you can download my thing and then use it. By the way, I will briefly mention about some files that can help you. I made something, for instance, this is the phi function I created, and as you can see, phi function is created this way. So from this to this is the phi function. And others I also created. For instance, if you want to solve some Diophantine equation, then you can just type ABC. A represent AX, A right coefficient of X, B represent coefficient of Y, and C represent the right side. So ABC, then you can get the answer. It checks whether a solution exists or not. If the solution exists, then it will give you the solution. If solution doesn't exist, it will say. For instance, I will run it so that you can see it. Diophantine equation of, for instance, 131x plus 726y equals 1 or maybe 11. Assume that you are asked to solve this problem, then you type it, then you will find the solution. So I create this one so that you can solve it. And then I also create a Chinese remainder theorem. You are asked find some x satisfying these things with modulus 10. For instance, the remainder is 3, right, with modulus 10. And then with modulus, for instance, what modulus do you want? 7. The remainder could be 5, right? And then you can write down as many moduli and the remainder in this fashion and then run it. Then it will give you the answer. Comma isn't the reason, because I create this thing in the sky, literally in the sky. I couldn't post this thing on the web, so I will download this. So it took the whole trip to create this file. Because there is no file, it didn't run. So 33. 33 is the one satisfying two conditions. With modulus 10, it has remained a 3. With modulus what? 7, it has remained a 5. 28 and the remainder is 5. Do you see? So these are the things that you can use. And also phi function. But as I mentioned before, it took the whole trip to create this Chinese remainder theorem, because as you can see, it is not like the other case such as Diophantine, or as you can see, it's very long, right? It's very long. In any case, these will help you understand the idea or usefully find the solution. In any case, I will prove all the facts that I mentioned. First of all, how to efficiently calculate phi will be mentioned. Because of the efficient method, I could create this kind of file, right? Because of the efficient algorithm, I could create this kind of file. Without the efficient method, how can I create this kind of thing? It's impossible, right? So there is an efficient way of calculating it. Second thing is the facts such as this even result, right? For any n greater than 2, Euler phi function gives us even result. Now check 6. Check 6. 6 is what times what? 2 times 3. Then find phi of 2 and phi of 3 and then multiply. So can you guess whether this function satisfies a very important thing or not? Can you guess it or not? This function is multiplicative. Check it. For instance, 10. 10 is what times what? 2 times 5, right? 2 times 5 gives 10. What else? 14. 2 times 7, right? 2 times 7. What else? 12. 12 is 4 times 3, right? 4 times 3. 8. 8 is just 8. 8, and then what? The next number. Prime power cannot be decomposed further.
What about
9 is prime power. 3 to the power of 2 cannot be decomposed any further. Multiplicative function doesn't have to satisfy for all pairs. It should satisfy for the GCD1 pairs. 3 and 3 has GCD3, so it's not. Or 2 and 4, 4 and 2, or anything has GCD greater than 1. No. Only when GCD is equal to 1, then multiplicative is okay. So I mentioned a lot of things for these examples, and important thing is not a few examples, because if you submit these things by calculating up to 1 million, the journals will reject your paper. No matter how hard you try to make own book-like paper and send, they will reject. We don't want to find these things for a specific number, for instance, 2008 or something. We want to prove this thing for whole case. So unless you stop me or you question me, I will continue. First thing, first. As someone mentioned, phi of prime is very trivial. Phi of p equals p minus 1. Why? All numbers except itself is relatively prime because prime doesn't have any other factor than itself or 1, right? So all other numbers are okay other than itself, right? In this system, right? If we exceed, then it returns back. So between 1 and p, only p is excluded, so p minus 1. So not increasing or neither increasing nor decreasing, right? And just counter example will be enough, right? The phi function is not an increasing function. Counter example will be enough. For instance, show these triples, then it provides a counter example for both. It is neither increasing nor decreasing, right? Right? These triples are enough. Then the next thing is calculation of these things for specific case. Prime power. Prime is already done. What about prime powers? Because for general n, it is very complex. We want to focus on prime powers. So what is your guess? Right? So numbers 1 through p to the power of k, then how many divisors can you find? One divides p, how many numbers have GCD greater than 1? 1 is disqualified, right? It should be greater than 1, right? Between 1 and p minus k, p to the power of k, how many numbers are disqualified? So I will write down the number that is disqualified. P is disqualified. Do you see it? 2p is disqualified. 3p is disqualified. All the way up to p times this is disqualified, right? Do you see it? These numbers are disqualified numbers. All others are okay because other than these numbers, there is no chance that GCD is greater than 1. Only something having p are disqualified. Then how many numbers are boxed? Can you count the boxed number? So boxed numbers what? P to the power of k minus 1 numbers, right? Boxes have, right? Boxes have. There are p to the power of k minus 1 numbers satisfying GCD of number and then p to the power of k greater than 1, right? Do you see it or not? If you don't see it, stop me. I will count it with you. So assume that you have, for instance, 2 to the power of 10. Then total 2 to the power of 9 numbers are disqualified. 2 to the power of 9 numbers mean 512 numbers among 1,024 numbers. So all even numbers are disqualified. If you don't see it or cannot count, ask me. So because of this, if we just collect something that is not disqualified, how many numbers are not disqualified? Among p to the power of k numbers, how many are not disqualified? P to the power of k minus p to the power of k minus 1 numbers are not disqualified. Do you see? If you don't see it, ask me. This is very important. Using this, I create the algorithm calculating p function. Is it clear enough? So some example may help you. 2 to the power of, for instance, 8. Then phi of 2 to the power of 8 is 2 of p to the a minus 2 to the power of 7. Then 2 to the power of 7 is a common factor. Then 2 to the power of 1 minus 1. Then it is 2 to the power of 7 times 1. 2 to the power of 7. So total 128 numbers are there. So let's check it. Phi of 2 to the power of 8. Total 128, right? 120. As I mentioned before, MATLAB doesn't have built-in p function. So if you type p function, you will get an error. So download the file and then run. Do you need more examples? If you need more, I can do it. For instance, phi of 3 to the power of 3. Then 3 to the power of 3, and then disqualified numbers, 3 to the power of 2. 9 numbers are disqualified. So total 27 minus 9, and it's 18 numbers. 18 numbers are qualified. Phi of 3 is cubed. 18 numbers are qualified. My program doesn't really count. My program doesn't really count. My program uses higher level theorem that we will cover very soon to calculate this. So if you need a visual proof, I will do it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, total 27 numbers are written, right? And then anything having GCD greater than 1 with this number should be disqualified. It's 3 cubed, right? So any 3 should be disqualified, right? Any 3 multiple should be disqualified. Then count the remaining numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? I verified it, right? So one more time, when we have prime power, it's very easy, right? Phi calculation is easy when you have prime power. Then the next question, assume that we know that n is p to the power of k and then q to the power of l. What would you do? Say it clearly, loudly. Yeah. If phi is multiplicative, then what happens? Phi of n equals phi of p to the power of k, q to the power of l, right? Then, because the function is multiplicative, p and q are distinct primes, phi of p to the power of k, phi of q to the power of l. Once we reach this level, then this is trivial because of the above fact. Then it is phi of p to the power of k minus p to the power of k minus 1, and then q to the power of l minus q to the power of l minus 1. Do you see? No matter how many factors are here, we can use this principle all the time. But there is one big problem. How can we prove this thing? And this will be questioned on the exam. I will prove it, and then I will ask this thing, as many times as possible. Exam 2, exam 3, final exam, anywhere. So I will approve it today, but this will guarantee this kind of calculation. But before going any further, if you have any questions or doubts, ask me. I will assume that this is multiplicative in the following statement, and next time I will prove it. So please ask question. Unless you ask a question, I will mention about one more thing. So this is nothing but p to the p1 to the power of k1, p2 to the power of k2, and then pr to the power of kr. Then it is phi of p1 to the power of k1, and then phi of p2 to the power of k2, and then phi of pr. This is what I mentioned. And one more thing that I want to mention is, if n is greater than 2, phi of n is even. So this is the statement I will prove with using the fact that phi is multiplicative. And later I will prove phi is multiplicative. But before going into this part, I will write down the result of the previous thing. It is what? This is what? P1, and then what is the result? Power K1 minus what? P1, K1 minus 1. And then this is what? P2, K2 minus P2, K2 minus 1. All the way through PR, KR minus PR, KR minus 1. And if you factor out P1 to the power of K1 from the first part, what do you get? If you factor out this thing, and 1 minus 1 over P1, do you see it? Do you see it or not? If you factor out P2 to the power of K2, then it is 1 minus 1 over P2. And the same thing happens, PR and 1 minus PR. So we can collect all these things. I will move this down. If you collect these factored things outside, then it is P1 to the power of K1, P2 to the power of K2, all the way up to PR to the power of KR, and then 1 minus P1, 1 minus 1 over P2, and then 1 minus 1 over PR. Then what is this number? Look at the starting point. N equals this thing, right? So it is N. And then 1 minus P1, 1 minus P2, and then 1 minus PR. Using this fact, we can easily calculate the phi function. So find the factorization. After finding the factorization, we just multiply n by these things, right? After finding the factorization of the number n. So instead of proving the case that I mentioned, I will give you more examples, and then the next time I will prove that the phi n is even for n greater than 2. But now let's use this example to calculate the thing that we did before. Phi of 12. Phi of 12 equals phi of 4 times 3, or 4 is 2 squared times 3. Then, because of this fact, 12 is written. And then 1 minus 1 over, first prime is what? First prime is what? 2. And then second prime is what? 3. This is it. So 1/2, 2/3. So 1/2, and then 2/3 are multiplied, and finish the calculation and get 4. So once you prove the important fact that the phi function is multiplicative, we can get many, many nice things. But as I mentioned before, the biggest hurdle is showing that the phi function is multiplicative, and next time I'll prove it. Let's stop.